Yeah. Hello, everyone. Welcome. This is Papers We Love. Thank you for coming. If this is your first time, welcome. If not, welcome back. So tonight, we are talking about Macaroons, which is a research paper that came out of Google 2014, I believe, so just last year. And this is the subtitle is Cookies with Contextual Caveats for Decentralized Authorization in the Cloud, which is a really long title that I'll get into what that actually means. So me, I'm Sam. I'm an engineer at Yahoo, and I also organize this in my spare time. I love reading papers. I love just learning computer science. Yeah, moving on. So I guess I'll cover what are macaroons at the beginning. Most of this paper is sort of a history lesson. I think that technology in isolation is boring. I think that when you look at cool solutions and you don't know anything that led up to them, you say, okay, like this is what we have, and you don't understand how cool it is. You know, cookies, we've been trying to do this for 20 years, and I think that it's really cool, the solution that this presents. So a macaroon at its core is basically a data structure that is tied to a location and has an identifier. So the location is basically who created this macaroon. The identifier is just how that location can verify it, and then the signature is just to sign the whole thing to make sure that it hasn't been tampered with. But let's back it up and say, how did we get here? Which is sort of a useless question unless, you know, we don't know where is here and what are we actually trying to do. And what we're trying to do is we're trying to more securely allow people to access content and share content on the internet. We want to protect data that needs to be protected, but also make everything easy, because people won't do it if it's too difficult. So once upon a time, there was this thing, and it was called HTTP, and so you would send a response or a request, and you would get back this response. And so people said, you know, how do we let users kind of keep a certain amount of state that they can store, but they can pass to the server? And so they said, great, we'll add this set cookie header, and you can, you know, do like little pairs of like, so this particular user wants a lighter theme rather than a darker theme, so it's easier on their eyes. You can do things a little more complicated. So you can set a session ID that the server knows to look up, and give it an expiration date. That can be really far away. It could be, you know, tomorrow. And then we created a thing called document.cookie in the browser. And that's a lot of fun because you can build your cart locally, and then when you go to checkout, you can just take your cookie and send that, and the server doesn't actually have to keep track of who you are. The downside of this is that if you are storing all of your session data locally and posting it, you can't synchronize sessions across browsers. So this is stuck in, like, you know, your mobile phone. You can't look on your desktop even if you're logged in. But it's fun until it isn't, because document.cookie is like, that's a global object. And it's really hard to secure web apps when you are including JavaScript that you didn't write on the page. And so eventually, if someone can cross-site script into your application, they can read that you know, session ID, and then they can just navigate to a different page. And maybe that other page just kind of takes note and sends you right back to where you were. But it's dangerous. So the browser people got together and said, great, we will call this thing HTTP only. And that basically removes document.cookie because you only send it over HTTP. And so people liked that. And then this thing, I don't know if any of you remember an app called Firesheep. It turns out that social networks weren't using secure channels to serve your requests. And so somebody wrote an app that could browse your network and just pull cookies out. And so even though you had HTTP turned on, people could just pull cookies and then set them in their own browser, and congratulations, you are Ian Gallagher. And so the browser people got together and they said, great, we'll add this word secure, and that'll fix it. Which, it's more than adding the word secure. It makes it so that you can only send cookies over HTTPS, but it feels funny saying, okay, we'll just append the word secure, and that will make it so. So security is hard, and I blame it on these 4 letters. I think auth is probably the worst abbreviation that we could do as an industry, because what does auth stand for? Is it authentication? Is it authorization? Because these are not the same. But if you Google either one of them, I searched for authentication. And it told me, authentication is a process in which credentials are provided, blah, 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 checked against a database. If the credentials match, the process is completed and the user is granted authorization for access. Which, yes, the professor is shaking his head. Right, and so, but when you search for it, this is the little box that comes up. So we've got a problem. So authentication is, how do I prove that I am who I say I am? So I can go anywhere and say I'm Sam. I could go anywhere and say I'm Mike, and people would have to have some mechanism of saying, oh, who are you? In the real world, that's a driver's license, it's a passport, a birth certificate. But authorization is, how do I prove that I'm allowed to do this particular action?
And if I search Yahoo, the first result on what is authentication comes from techtarget.com and says, authentication is a process of determining whether someone or something is in fact who or what it is declared to be. So
you should all use Yahoo
gets it right
instead of Google.
Yahoo gets it right.
Right. And now, so at some fundamental level, they're connected, because, how do I prove that I'm allowed to do this? How do I prove that I am allowed to look at this image on Facebook? And Facebook will go and say, who are you? And you'll authenticate, and then they will check their access control list and say you are not authorized or you are authorized. So there is a connection, but they aren't equivalent. So if we go back and we say, once upon that same time, back when there were no cookies, we were on networks where people knew each other. And so the internet was small enough, you could say, I'm Sam, and people would kind of know who that is. Your eyes are very large.
Remember this time. Don't remember this time.
Right. And so, but because you're out in cyberspace, I think they called it back then, you would say, I am this person, and I can do this wasn't that big of a jump. And so people came up with certificates like the 509X or X509 cryptography. You would get a public key and a private key, and so you could prove that I am this person. And so really it was all about linking your online identity to your actual identity. And so people basically tried really hard to come up with ways to do this and ways to use this. There was a project called SpookySquid, which was actually two projects. One was Spooky and the other was Sudsy. They realized they were trying to solve basically the same problem in the same way, and so they teamed up. And so they came up with a way that you could use your certificates, your public keys, to issue other certificates that would then have attributes about you. And so, for example, this person, they are issuing a certificate that people can verify that demonstrates that this is Carl Ellison. You can tell a bit that it's aged because this is an example that uses MD5 cryptographically, at least claiming to. And so,
Nothing, sorry.
And so the requirements documents for this project are actually really cool. They're out publicly on the IETF website. And so some of the examples that they were trying to solve for are, I want to sign a contract to buy a house. What type of certificates do I need? Well, you're going to need an authentication certificate because you can't buy a house anonymously. You're probably going to need some way to demonstrate that the bank has authorized your mortgage. You'll need another certificate saying that the buyer or the seller has accepted your offer. And then you'll need to have something that ties all of those together. Or I'm a sysadmin, I want an ephemeral way to grant me root access to certain systems and maybe just for today. So let's say you need access to a server to send notifications just one morning, but don't need it any other time of the year or ever. You can do that. Or you might be an agent of a company and you don't necessarily want to be identified, but you do want to prove that you are permitted to spend up to X dollars of a company's money. So you would have to have a certificate and present that to whoever you're buying from, and then when they exchange money, they can send that back to the company and say, this person said they were authorized, and the company can say, yes, they were. And, so those are basically the types of, at least the most interesting types of use cases that SpookySquid was trying to solve for. This isn't by any means a complete list. There are all sorts of, can I issue a birth certificate electronically? Can I prove that I am licensed and permitted to issue drug prescriptions? Or maybe I could have an online Blockbuster card was one of the examples. So skip forward because SpookySquid was, I want to say the late 90s, the early 2000s. It didn't really catch on because it was very complicated. Again, these certificates, where is it? These certificates were huge, like S expressions, and they almost looked like Lisp programs, and so it didn't really catch on because it was complex.
You're at 1996.
1996. And so fast forward, it's 2015, nobody's heard the words SpookySquid in decades, and I believe the one major implementation actually was admitted into the Smithsonian as a historically significant artifact, but not a historically useful artifact. Right. And those people worked really hard and they did really cool things, and they were trying to solve the right problems. They just didn't solve them in a way that everybody wanted to use. So fast forward, 2014, Google releases a paper on macaroons, which it's a play on cookies. Macaroons are better than cookies, depending on what types of cookies you like. Anyways, so macaroons basically take all of those things that you want to say, which are caveats, you say, you know, this certificate is valid as long as I can demonstrate that I'm the person listed as buying the house, as long as I can demonstrate that my mortgage has been approved, as long as I can demonstrate that the seller is selling to me, then we have a contract. And so we can chain those, and we can add on additional caveats. And I put encoding a domain-specific language because Macaroons doesn't specify how how these caveats actually need to look. It just allows a way to embed caveats. So basically, you can create that macaroon, and you remember the initial one. It had a location, it had an ID, and it had a signature. And so this is that initial macaroon. You just don't tell people the secret because that's how you verify as the issuer. So you give that out, and then you can take that macaroon and you can add a caveat. So say this web request is only valid if the user is Emily, and you've got a new signature, and you've got a new macaroon. And so you can give that macaroon out publicly. You can post, I don't know, if you encode this in like base64 and stick it on the URL, you can give this out to anyone, but only the user Emily will be able to log in. And the way that this would work is basically the server, when you send the macaroon back to verify it, they would take the location, the ID, they would look up the secret that they've stored, they would hash it, add the caveat, user equals Emily, hash it, and as long as those signatures match, it's a valid macaroon. And so you don't need to tell the issuer every time you add a caveat. It's just sort of magic. And so you can give that to Emily, or maybe you can say, well, I don't want Emily to write to the service. I only want her to be able to read, and I only want her to be able to read my cat GIF. So you can make a publicly accessible URL that only means anything to one person.
How do the secrets get exchanged if the other side that you're sending the macaroon to needs to rehash and do the same thing? Do they know your secret?
Well, so they don't, basically. So what would happen is I would mint, or I don't know, run a bakery that issues macaroons. So I would basically be the end service. And so there might be another service that would want to use me as storage. I would give it to them. They don't need to know the secret because they can give it out to their users. But they ultimately need to bring that macaroon back to the original location. And only that location knows the secret, except for if it's a third-party macaroon, which I will get to.
But two people have to know the secret. This is a shared secret, or this is not a shared secret.
In this case, it's not a shared secret because you are creating the macaroon and it doesn't.
Creating the whole first macaroon, the first secret.
Right. Okay. You don't share that secret.
And you can give that.
You give that macaroon to users. And they can share that, and they can add their own caveats. But ultimately, in order to actually...
Only you have the secret, so when they're giving you... Okay, got it.
Right. So, and you can't verify a macaroon without the secret, because the hash won't make sense. So basically, there's a JavaScript library called MacaroonJS, very creative. And so you can create... Can everyone read that, by the way? Can people see? So basically, we've created a location, a secret key, and an ID. And then you can build a macaroon. And then you can basically assert that this macaroon is valid for this key. So if you run it, it doesn't die, and it prints out what we would expect. But we can make that more complex by creating that macaroon. And let's say in this step, we pass it to someone else. They can take that and append to it. So we can add those caveats and get a totally new macaroon. And if we run that, it'll panic that verification failed because we didn't actually satisfy these. And so if someone else comes and they are, user is, I don't know, Emilio, then that would fail. And so only once all those caveats are satisfied does the whole thing work, and you can authorize them. Now, whether or not requesting catgif as Emily makes any sense is a whole other question. There might not be any catgif. You could also embed, if you're running a service and you're spiteful, you could append like true equals false, and that will never be satisfiable. So you're essentially you're teasing.
Does the order in which you apply those things matter? Because you always use the same signature each time. Are they?
So it does internally in terms of this library. It doesn't. Essentially, you can satisfy exact. And this monitor is going out.
Yeah.
Okay. Oh wait. Oh, this is Windows. Pressing all the wrong buttons. So we can.
I had the same problem.
We can say, hey, we'll also satisfy dogGif, and so what you're essentially saying is you are telling the verifier, here are a bunch of things that I am willing to say are true about this macaroon, and then it's up to the verifier to look at the macaroon and figure out what actually it needs to hash and in what order. So if we look at this, it will add these caveats in a specific order, and it can iterate over those and hash them to make sure that you do get the same signature at the end. Does that make sense? So here's a potential architecture. So you have some database, and it might be like your AWS or your whatever cloud storage solution you have. So they will issue a certificate or a macaroon to, let's say you're running a forum, and I am shamelessly stealing this example from a presentation by one of the authors. But they can issue this macaroon to the forum website, and the forum website can say, great, I'll use this to authorize users, and say, oh, except I don't do my own login. I've dispatched that out to microblog or Twitter or Facebook or whatever authentication system they have. And so they pass the macaroon, they add a caveat saying you have to be logged in at microblogs. And they send that to the user. And the user looks at it and says, oh, this says I have to be logged in at microblogs. So they go there, they prove that they are that user, and microblogs will give them back another macaroon. And then they combine those two macaroons, and they send them off to the storage. And the storage can look at it and say, great, you've proved you're logged in, you've proved that you're a forum user, here's your picture, or here's your blog post, or whatever. And so now the forum and the microblogs do need to share a secret, because you do have to have a way to prove that microblogs is issuing things in the same way that the forum is, if that makes sense. Am I just
reminds me of OAuth.
It is, yeah, exactly. It should, because this is
it's the same idea.
It is the same idea, and you can actually sort of replace OAuth tokens with macaroons.
Replace everything with macaroons.
You
Is
could.
that the idea? Yeah.
Right, that's the idea, is that this could be used instead of cookies, this could be used instead of OAuth. Like imagine imagine a social network where you don't actually have to log into that social network. You can be running your own authentication server and have a different storage server and a different friend server. And you can share pictures, and you can say, this is a list of people that I will share this with, and just post public URLs. And those people will have to bring their own proof. And so you don't have to keep all your access control lists on the server. It's a bearer's token, but because it's signed, you can verify that the bearer token is real.
You could throw an awful lot of caveats on these things, though.
Yes.
And sorry, I didn't read the paper, so.
No. And that's actually one of the coolest things is you can tell microblogs that you care about certain caveats, and so it's like don't issue a macaroon unless these conditions are met. But because they're issuing a macaroon, they can tack on their own caveats to that. And so you can get back something from microblogs that says, yes, you're authenticated, but this is only valid if you check with this other service. And so you can build all of these proofs. And like if you're familiar with formal logic and like building proof trees, you're essentially saying like this is valid if this is valid, but that's only valid if this is valid.
So you got authorization mixed in too.
Right, and so it isn't decentralized, or
well, in the sense that people will be able to understand each other's macaroons.
Yes.
I still.
So you do need a common language to encode caveats. You need some way that service A knows what service B's strings even mean.
Sure.
Yeah. When you do send things over to microblogs, I've been talking a lot just hashing. The paper talks about performance of different hashing. The idea is they need to pick an algorithm that people can implement everywhere, whether it's embedded services, phones, or even web browsers. And so they picked SHA-1 because it's really easy. You might remember that a few years ago somebody managed to get a SHA-1 collision almost using like a supercomputer over a couple of weekends. So there was an update to that paper by the same people, and they said, we have provided free start collisions for SHA-1. And it says this is the first practical break of the full hashing algorithm, taking only 10 days of computation on a 64 GPU cluster, which this is commodity hardware in a very reasonable amount of time. That should scare you, but not the authors of the paper, because they said just add a caveat that says this is only good for like the next hour or the next minute. Actually, they've discussed that baking macaroons should be so easy and so cheap that you can do it on a per request basis. And so when you generate a page and there are a bunch of links that need to be protected or authenticated or authorized, you can make like 10 macaroons and just give every different URL a different macaroon. And you could say like, this macaroon is only good if no one has ever tried to access this page before. And then you just discard it. So it is using a hash that makes people nervous, but they're not using it in a way that should make people nervous, if that makes sense. Eventually, we'll probably get to the point where we can just break SHA-1 very quickly, and that's terrifying. But I think by that time, we'll have just found a way to say, okay, this is a macaroon that uses SHA-2 or SHA-3. Or And that's basically what I have. There's some further reading on the spooky requirements. You can read the paper on free start collisions. It's not too long. Did any of you read this paper? It's fine if you didn't. See a few people nodding.
I read
Hands
some
raised.
of it, most of it.
Some people printed it out. Maybe used a highlighter. Okay, cool. I mean, does anyone have questions?
I guess I still think that these things really have to be done in order. First you start off with, what do we start off with? The location, the identity, and the secret.
Yes.
That gives our first signature. Every time we add a caveat, we use the previous signature. They're all chained together. So
Right.
how is it that you can come up with a system where order doesn't matter? And how can you come up with a system, or can you ever come up with a system that says, here's something with these 3 caveats? Is it always all 3 caveats must be?
Yeah, because if they remove them
Always.
and they
it's
hash
always
the
there.
caveats, then it'll be obvious that something's missing because it won't.
Okay, so that we don't have to worry about subsets of caveats or any kind of logical ors. It's always a bunch of ands for the caveats. The way these are intended to be used.
Yeah. It's always an and.
Fair enough, but then in order to check the final signature, you have to hash it seems like you have to hash the caveats in the same order. Or how do you know what caveats?
You would. They are encoded in an order. It's a list, but it's an ordered list.
So there have to be a kind of protocol or agreement that says, I have a bunch of caveats, but they have to be supplied in a particular order. Like you said, the user was Emily,
Yeah.
and the date was less than something, and I'm looking for a particular resource. Okay. But you've taken all those caveats, you hashed them, you have one macaroon.
Mm-hmm.
When the macaroon is sent somewhere, how does the other side know what to check? How does it know to check for the user Emily? Because
Like, how does it know, like, in checking that order?
How does it know to check in that order? How does it know?
You mean when you
what
send
to
it
check?
back? Like if you
Yeah.
send it back to the location to be verified?
Oh, so
Because
that
only the location knows
yeah.
the secret, and so only the location can actually verify. And so you're
And then
sending it over the
location
wire.
Then the location knows what it needs to look for.
Knows the recipe, if you will.
Yeah, or you could basically create. So for example, there's a satisfy exact where you can just stick like a literal byte string, and so that would be great if you are maybe saying I am asserting certain headers like the browser or the language. But you can also have like general satisfiability or general verifiers that can read the string and parse it. And is that unrelated to your question?
No, it's who does the verification. I mean, when I think of there's two-party verification, but then you said it sends it back to be verified, and then there's a single place.
Right, and so
then that makes sense. I was thinking more in terms of the two.
Well, so if you add a third-party caveat, there's a shared secret, and so basically you would come up with a secret and say and associate it with certain caveats that you want the other service to care about. So, for example, I could tell microblogs only accept, followers of this person, or accept all people who are logged in.
So that you tell the microblogging service first. You have to communicate that to them.
Right.
Then
and
you're
so,
going to send them a macaroon that they're going to check against. Right?
Well,
they
you
verify.
don't send them a macaroon. You can just send them. It's not specified.
Okay.
You can send them a list of here are things, conditions that you don't issue unless these are met, and you pass them a secret, and they could pass you back an identifier, and so then you take your macaroon, and you say, great, here's a third party, this is its ID, and it's on this other server. Go check with them.
Mm-hmm.
And so then they can go and get that macaroon by ID And the server
That's
might
the-
say yes, or it might say sure, but this is valid in the past.
Okay.
Yeah.
Okay.
So, I don't know, I think it's cool because it's not a complicated technology, but it's amazing how many use cases it can solve for and how many things you can do. In the paper, it talked actually pretty extensively about its relationship with the SpookySquid research. And they said these are proven equivalent. There's nothing that Macaroons can do that the other couldn't, but it's easier. Because you can look at this and you can read it and you can understand it. You can do it in JavaScript in the browser.
Yeah, the paper said there was like some constraint when comparing to those, but I forget how it said. It said it also elaborated on how it could get around that constraint. I forget what it was though.
Which
when they were comparing to like Sudsy, Spooky, whatever, they were saying like there's a key difference, like a drop, like sort of like a drawback that can be worked around or something.
Oh, I think that might have been that the SpookySquid sort of revolved around like longer running secrets.
Okay.
But this very much operates under the assumption that you will not reuse a secret. So you should come up with a random string for a secret and then only use that for one and not have that as like your server secret.
Yeah.
Cool.
So, Andy obviously read the paper, but I didn't. But so when was this from? Like when was it published?
When was
year?
this published? 2014. So
Okay.
last year.
Is anybody using it? Like
Google uses it. What's it called? Rackspace. They use it to do lots of sysadmin stuff and to authorize their own services internally.
Interesting.
Yeah. And from what I've heard, Google uses it decently.
I like that it's not part of it's not reliant on HTTP or anything. I mean, this is any app.
Right.
You can do this. This is mobile. You can share it among your.
And they don't even specify a way to transport this over HTTP. So you could put it in the request body. You could pass it as a custom header. You could put it in the URL.
You don't even need HTTP. I mean, you just pass it over your own protocol.
Yeah, you could
Never
secure
stop
your
it.
Gopher servers.
Yeah.
Or secure your BBS. Yeah. So that's
Why did people not like Spooky and Sudsy? Was it the S expressions?
I think it was the S expressions and the word certificates just sounds official. Like feels like there's a lot going into issuing a certificate.
Not fun and tasty.
Right, something that you have to like call a salesperson about, and I don't know.
Right.
Yeah. Yeah, so that's what I have. Thank you all for coming.